After receiving this knowledge injection, you will know what a 3D mesh is and how it's constructed. We're gonna cover a lot of stuff, so get ready. What is a 3D mesh? A mesh in 3D terminology describes a structure of points, edges, faces, and additional data which form the shape of an object that can be processed and visualized by a computer. The accurate term is polygon mesh, because the interconnected faces that make up a 3D model are called polygons. Meshes are used for 3D rendering, which is probably the most popular use of meshes, 3D printing, product design, architecture, and many other things. You probably remember those dot-to-dot pictures from your childhood. Meshes work pretty much the same way. If you connect 3 or more points with a loop of straight lines, you end up with a polygon, a closed shape defined by well-defined points and sides. A single point of a polygon is called a vertex. Multiple points are called vertices. Remember that. One vertex, multiple vertices. Way too many people get this wrong. You don't want to be one of those. If you take a vertex and connect it with another one, you have an edge. Connecting multiple edges in a closed loop defines the polygon's face. Polygons can be connected as well. Simply by adding one more vertex, we're able to define another complete polygon that partially shares the same vertices with the polygon we defined earlier. Changing the location of a shared vertex implicitly affects all the polygons that are connected to it. As you might have guessed, this kind of structure is called polygon mesh. By connecting many polygons, you can create any arbitrary shape. From animals to human characters, buildings, spaceships, all sorts of everyday items, or simply abstract shapes. An essential piece of information to describe a mesh is the vertex data. In order to be able to locate a vertex or anything else in 3D space, we utilize a 3-dimensional coordinate system with the axes x, y, and z. The exact meaning of those axes may vary depending on the software or mathematical concept you're using. You should always know whether you're dealing with a left-handed or a right-handed coordinate system and which axis defines the vertical axis. Using such a coordinate system allows us to precisely specify the position of a vertex, which is the most essential piece of data, commonly represented by a 3-dimensional vector. Vertices might also have an orientation in 3D space. This orientation, which in mathematical terms is called normal, can be imagined as a line which originates from the vertex and points in a specific direction. Vertex normals are vital for light computation and for achieving certain shading effects like smooth shading, which makes the surface appear, well, smooth. Usually normals are stored as 3-dimensional vectors and they have a length or magnitude of exactly 1. This specific kind of vector is called a unit vector. A more tangible way to picture how the position and the normal of a vertex work together is simply imagining a pin whose head represents the position and the actual pin defines the normal. A popular feature of 3D graphics is texture mapping, which allows projecting a 2-dimensional image on a 3D model. The obvious use of a texture is applying color and visual structure, but there are many different types of textures which define various properties that influence the 3D model's appearance. Because there are virtually unlimited ways how a polygon can be projected on a texture, another coordinate system is required to precisely specify which portion of the texture is mapped onto our 3-dimensional polygon. The horizontal axis is called u and the vertical axis is called v, each ranging from 0 to 1. This allows us to define the position for each vertex in texture space. This piece of information is often called UV coordinate or UV for short and is represented by a 2-dimensional vector. Many 3D tools and game engines support multiple UV mappings serving different purposes. Light maps, for example, often require a different UV layout. The final piece of vertex data we'll discuss is a simple color value that, despite its simplicity, is very powerful. A common way of specifying a color in computer graphics is a group of 4 values representing the components red, green, blue, and alpha. In graphics programming, each component is often stored as a floating point number ranging from 0 to 1, but the corresponding values can be stored in several ways. Using a group of 4 bytes ranging from 0 to 255 also isn't unusual. After all, colors in a computer are just numbers which you can use for whatever you want. A vertex might also contain multiple colors serving different purposes. Okay, that was a mouthful. Let's recap. A vertex has a position, it might have a normal, remember the pin, UV coordinates to allow texture mapping, and it might have 1 or more color values. These properties are the most popular ones, but you could store any arbitrary data for each vertex. To finally create a complete mesh, we need a higher level data structure that holds information about how the computer has to interpret our vertices. There are several ways to store mesh data, but at a lower level of graphics programming, the following structure or a variant thereof is quite common. The vertices with all their additional data are organized in a sequence which many programmers call an array. As you can imagine, simply storing the vertices is not enough to describe a complete mesh. First, we introduce unique numeric indices which enables us to identify each vertex. In order to describe how our vertices are connected, we introduce another array storing vertex indices in groups of 3. This lets us define triangles and it allows shared vertices. Note that the connection between the first and the last vertex of a triangle is implicit. An important aspect of triangle data is the order in which the vertex indices are stored. The so-called winding order determines which side of the triangle is the front face. If the order deviates from what your engine or renderer expects, all triangles might appear flipped. Clockwise order seems just as common as counterclockwise order. I personally have seen both, so if your triangles appear wrong, the winding order might be the problem. As you might have noticed, the meshes we've examined so far exclusively consisted of triangles. There are some good reasons for that. A triangle is the only geometric shape that can be unambiguously oriented in 3D space. Triangles follow well-known and partially unique mathematical rules and are therefore easy to compute efficiently. Although computers like to work with triangles, 3D artists often prefer faces that consist of 4 vertices, so-called quads, which allows a more intuitive and pleasant workflow. Sometimes faces with an arbitrary number of vertices, called n-gons, can also be useful, but should be used with care. In many cases, the mesh data will eventually be triangulated, either manually or automatically, before it gets processed any further. Meshes can be created manually by using a 3D tool or procedurally by a computer program. There are also different scanning and photogrammetry techniques which allow capturing real objects and environments. Some of the most popular tools that are used for 3D modeling are Maya, 3ds Max, ZBrush, Blender, and Cinema 4D. If you would like to try creating your own 3D models right now, you might want to check out Blender, which is available for free. There are many different file formats that are used for exchanging 3D data between all those tools and engines. Pretty much all of them have certain advantages and disadvantages you should be aware of if you use them. The number of polygons, or the polycount, is an important thing to be aware of at all times. Because more polygons necessarily require more resources like memory and computation power, keeping a polycount as low as possible generally is a good idea. For photorealistic rendering, artists often create their models with a rather high polycount, which allows fine detail and smooth curves. Those high-resolution models that may contain millions of polygons are typically called high poly. Low poly models, on the other hand, are often easier to work with and because of their low polycount can be processed very quickly. Even though the polycount doesn't cause as big of an impact on real-time rendering performance as it used to, it still is an important factor for smoothly running modern games or other 3D content. Unfortunately, there's no good rule of thumb to determine the optimal polycount for a particular purpose, because every 3D project has individual requirements and needs. Yeah, that's it. By now you should know a lot more about meshes than many other people. This was a lot of stuff, I know, but there's a whole lot more to learn about meshes. Hit up the browser of your choice and look up any term you haven't heard before or whatever caught your interest. There's always a way to know more problems.